All right, good afternoon. Again, today we're going to resume with inequalities, and we made a transition away from polynomial inequalities to rational inequalities. And I left off with a problem to work with involving this particular rational function, and I just want to add some layers in describing what we have for r of x and just sort of tie it all with inequalities compared to zero. And again, when we looked at stuff like the asymptotes, we looked at, say, like the domains of functions, especially rational expressions. And for this one, we have r of x is equal to x squared plus 5x plus 4 all over x squared minus 2x minus 3. And again, for rational expression, okay, the taboo number is 0 when it comes to the denominator. Okay, now you can have a 0 as the top value as long as you do not have 0 as also the bottom value. So for what we have for the domain, again, you always look for the domain before you simplify the rational expressions. So we have, first of all, we have with the denominator. Okay, we have x squared minus 2x minus 3 cannot be equal to 0. So anything in x that makes this equal to 0 is going to be off limits. So in looking at what we have in factoring this trinomial, so we got x plus 1 and x minus 3 for the factors of this trinomial. And so we have that neither x plus 1 nor x minus 3 can be equal to 0. And if x plus 1 cannot be 0, okay, so we have that x cannot be equal to negative 1. As for x minus 3, if that cannot be 0, then we have the x cannot be equal to 3. All right, so for the domain of this rational expression, okay, we have all the real numbers except for these two. Okay, so just applying the layers, okay, we have at the lower end, okay, with negative 1 as a smaller restricted value. You're going to have at the least end, you're going to have those values x in the domain to be those that will be less than negative 1. And again, x cannot be negative 1, so we're going to bypass this value. And we have next in line, okay, those values that will be greater than negative 1 and approaching but not including 3. Again, so 3 is off limits. And again, bypassing 3, and with 3 as the second and last restricted value, we're going to have the rest of the domain to be those values of x greater than 3. All right. Now, for what we have in terms of asymptotes, and again, our first asymptote kind was the vertical one, and this was originated, okay, from the restricted values whose factors remain in the denominator, okay, after their function is reduced to simplest terms. Okay, so for x squared plus 5x plus 4 over x squared minus 2x minus 3. Okay, if I factor, okay, first of all, okay, for x squared plus 5x plus 4, so this would go to x plus 4 and x plus 1. And once again, with factoring this trinomial, okay, so again, we have x plus 1 and x minus 3. And if you notice between the numerator and denominator, okay, we have x plus 1 in common. Okay, and so in reducing, it's going to turn out that x plus 1 completely cancels. And so with x plus 1 no longer in the denominator, okay, this is going to signal that there is going to be a hole at x is equal to -1. And for what we have in terms of the reduced form, okay, so we have x plus 4 all over x minus 3 and once again, okay, we have with x minus 3, okay, so x minus 3 remains. And since x minus 3 remains, okay, there's going to be a vertical asymptote at x is equal to 3. All right. Now, in terms of any other asymptotes, okay, this will come down to the comparison of the degrees in the numerator and denominator. Okay, so we have with this function, okay, so we have in the numerator, okay, so we have highest order term is x squared, and in the denominator, okay, the highest order term is also x squared. So we have that n is equal to 2 and m is equal to 2. The values are going to be the same. So we have that n is equal to m. Now, again, when we looked at situations where we might have a horizontal asymptote to arise or a slant asymptote to come about, okay, this will be contingent upon how the numerator degree compares to what is in the denominator. And now if n is less than or equal to m, you're going to have a horizontal asymptote. And since these values are equal, okay, there is going to be a horizontal asymptote. Now if n happened to be less than m, your horizontal asymptote would be y is equal to 0, which will be the x-axis. But now with the degrees equal, okay, the horizontal asymptote is going to be y equal to a non-negligible constant, which will come from taking the ratio of the highest order terms from the numerator and denominator. Okay, so here we have x squared from the top and bottom parts, and x squared over itself, okay, that reduces to 1. Okay, so we have a vertical asymptote at x equal to 3 and a horizontal asymptote at y is equal to 1. Okay, so again, we had two restricted values from the domain, and the restricted values, they were either going to become a vertical asymptote, which was the case for the value of 3, but if the restricted value has its factor to completely cancel from the denominator, instead of becoming a vertical asymptote, it will become a hole instead, as was the case with -1. And again, we have with the degree comparisons, again, numerator and denominator have the same power, and thus we have a horizontal asymptote, and again, this becomes y is equal to 1. And now, looking at what we have in the graph, okay, along with the asymptotes. So just looking at what we have and zooming in. Okay, so you have so you got r of x, x squared plus 5x plus 4 over x squared minus 2x minus 3. So you're going to have these curves in blue. So you have r of x is split into two different sections. And that is thanks largely in part to the vertical asymptote x is equal to 3. So this will be symbolized by the dashed vertical line. And again, this asymptote is off limits. And we also have running side to side. You have the horizontal asymptote y is equal to 1. And once again, we had that there was a hole at x is equal to -1. And it is situated right here. So you have a hole at x is equal to -1. So these are essentially the mechanics from what we have from the vantage point of the graphing, as well as the characteristics from which the graphing sections will be separated, and also where you have like some parts of the graph that will be cut out, okay, thanks to what we have, especially like in the case of the whole in the function. Now, for what we have regarding inequalities, okay, so just sort of hitting the reset button and looking at what we have with r of x. And again, just like with the polynomials, the rational functions, we're going to identify all the zeros once again. And so just looking at what we have now. Okay, so just looking at what we have in the setup. Okay, so taking what we have, identifying the zeros. Okay, so you have, we already have the domain and the asymptotes part taken care of. And just setting things up where we can set up a table to establish the zeros from which we can form the intervals. Okay, so with x squared plus 5x plus 4, again, we're going to have the quantity of x plus 4 times that of x plus 1. Again, we have all over x plus 1 times the quantity of x minus 3. And just looking at what we have with our factors in x. Okay, so you have x plus 4 is equal to 0. So if x plus 4 is equal to 0, we have x equal to negative 4. And then we have, for x plus 1, this one appears in both the numerator and denominator. And we have x plus 1 equal to 0. We have that x is equal to negative 1. And as for x minus 3 is equal to 0, we have that x is equal to 3. Okay. Now, again, just in the setup, going ahead and identifying the zeros that originate from this rational function. So again, we have r of x is equal to x squared plus 5x plus 4 we have again all over x squared minus 2x minus 3. Okay, now in the case of the zeros, okay, so we have first of all we have x equal to negative 4. And in this one, okay, so negative 4, this comes from x plus 4. X plus 4 is exclusively in the numerator. So if x is equal to negative 4, it will set this rational function equal to 0. And again, you can have a 0 numerator as long as you do not have a 0 denominator. So we can say that for negative 4, I'm going to use a little bit of shorthand here. I'm going to say ITD, as in negative 4 is in the domain. Now for our other zeros, okay, now we have negative 1. Okay, now negative 1, okay, you had this to steal from x plus 1. Now x plus 1 is in the numerator. And if it were only in the numerator, we could say that negative 1 is in the domain. However, the tiebreaker is going to send negative 1 as belonging to the category not in the domain, because x plus 1 is also in the denominator. And you cannot have a 0 numerator if you also happen to have a 0 denominator. Okay, so in this case, we have negative 1, we'll say NITD, okay, not in the domain. And as for 3 itself, well, this comes only from x minus 3, which is exclusively in the denominator. And again, for a rational function to be real, the denominator cannot be 0 in value. So 3 is also not in the domain. And if we look at setting up intervals around these zeros, regardless of whether they are in the domain or not. So we have here, have -4 is the smallest value among the zeros. So we have values of x less than -4. Then we have followed by values of x greater than -4 and less than -1. Then we have those values of x greater than -1 and less than 3. And then we have those values of x greater than 3. And so setting up our table, so I'm just going to create partitions separating the interval sections. So what we have going this time row by row. So after the establishment of the intervals. So I'll look at testing out each one of them by taking a sample. So we have starting out by taking a test value in x. So as a sample, for the first, we're looking at anything that is less than -4. So -5 is a possible choice. And then we have between -4 and -1. So we can select either -3 or -2 if you stay with the integers. If you want to go with the fractions, be my guest. Now between -1 and 3, you can choose 0, 1, or 2 among the integers. We'll just go with 0. And anything greater than 3, we can just select 4. And we have, once again, for the next item, and again, this is just the output which we have in the rational function. So looking at r of -5, r of -2, r of 0, as well as r of 4. So if I go ahead and take on r of 0, so what's going to happen here? You have 0 squared plus 5 times 0 plus 4 is 4. Then you got 0 squared minus 2 times 0 minus 3. That'll be 0 minus 0 minus 2, so that'll be -3. So we're looking at, in this case, we got 4 over -3, so r of 0, this will become -4/3. Now for r of -5, so if I were to replace x with -5, so I have -5 squared plus 5 times -5, we have plus 4. And in the denominator, so I have -5 squared minus 2 times -5 minus 3. Okay, so squaring out negatives. Notice we don't have any negative signs out in front of the x squared terms. And so I'm going to square all of -5. So the square of -5 is 25. 5 times -5 is -25. And we have followed by the addition of 4. And we have in the denominator. It's got -5 squared is 25. -2 times -5 is going to be a positive 10. We have -3. So here we have, so we got 25 minus 25 plus 4 is 4. 25 plus 10 is 35 minus 3 is going to be 32. Okay, so for this ratio, okay, that is going to reduce to positive 1/8. Now for what we have in the case of r of -2, okay, so I have the square of -2. We have plus 5 times -2 plus 4. And we have for x squared minus 2x minus 3. Okay, so we have here, okay, so you have -2 squared. Minus 2 times -2 minus 3. Okay. So you got 4 minus 10 plus 4. Okay, so you have from -2 squared, so you have 4. -2 times -2 is a positive 4. Then you got minus 3. So you got 4 minus 10 is -6 plus 4 is -2. And 4 plus 4 is 8 minus 3 is 5. So we have -2 over 5. So right away this will become -2/5. Okay, and as for what we have in the case of r of 4. Okay, so you have 4 squared plus 5 times 4. And we have plus 4. Okay, and again we have all over. You got 4 squared minus 2 times 4 minus 3. Okay, so you got 4 squared is 16 plus 20 plus 4. And we have, again, so we have 4 squared is going to be 16. We've got minus 8 minus 3. And so we're going to have 40. 16 minus 8 is 8 minus 3 is 5. And we have for 40/5. Okay, so this will become positive 8. All right. And so we have in the case of the values. Okay, so for what we have in the case of the sign of r of x, okay, so anything that is plugged in for x, okay, that is less than -4, okay, the output is going to be positive. Okay, so we have the r of x is greater than 0. Anything from the next, okay, we have a negative output. So you have the r of x is less than 0. And next we have r of x is less than 0. Then Then we have for the last case, you have positives. Case you have R of x is greater than 0. All right. So we have here. So we have among the comparison to 0 inequalities. And what I will do here, okay, so I'm just kind of go back to here. Okay, so this is our rational expression. Okay, so whenever we have now R of x, again, R of x is x squared plus 5x plus 4 over x squared minus 2x minus 3. And whenever this ratio is less than 0, now what we're going to have for the interval solution, now because the inequality does not have the equal sign, your only grouping symbols will be parentheses. So where R of x is less than 0, we have, okay, so you have in the middle two interval sections, so you have those values between -4 and -1, and you have along with those values of x between -1 and +3. Now, if I have that the rational expression is less than or equal to 0, okay, so we're looking at the same direction as less than 0. Okay, and now with the equal sign, there is the potential for there to be brackets in the midst, but it's no guarantee until we look at what is in the domain and what is not. Okay, so for -4, okay, this is in the domain, so that part will make this ratio equal to 0. So -4 is part of the solution, so this will be in the bracket. Whereas -1 and 3 are not in the domain, because if you plug -1 or 3 into x, your R of x is going to have a 0 denominator, so instead of equaling 0, R of x is going to end up as undefined. Okay, so -1 and 3 are not officially part of the solution, so those are going to stay in parentheses. So again, just doing a bit of color coding. Okay, bracket for in green for in the domain, and then not in the domain I have red, okay, with those enclosures around -1 and 3. Now, for R of x is greater than 0, okay, so where we have greater than 0, so you're looking at the first and the last interval sections, no brackets to deal with here since they don't have the equal sign. So we have those values of x less than -4 along with those values of x greater than 3. Now for R of x is greater than or equal to 0. Again, same direction, is greater than 0. And we are involving, okay, the same values, okay, for the intervals. Okay, so again, infinities are boundless. So we have negative and positive infinity, still in parentheses. As for -4 and 3, -4 is in the domain, and that creates the equal to 0 part. And again, 3, it does not create the 0 equal to 0 part, but instead renders the function undefined. Okay, and so around 3, again, we have a parenthesis. So this will complete out, okay, what we have among the interval solutions, where we have our possible comparison to 0 inequalities with our function r of x equal to x squared plus 5x plus 4 all over x squared minus 2x minus 3. Okay, now, and looking at what we have in the case of comparison inequalities. Okay, say we have r of x is equal to 1 over 2x. Okay, now for the zero of this, okay, you have only one variable expression, that is 2x. And from this, okay, we have that x is equal to 0. So this is the only 0 we have from this rational function. So r of x is equal to the reciprocal of 2x. And the only 0 we have, again, is going to be 0. And guess what? 0 stems from 2x, and 2x is situated in the denominator. So 0 is not in the domain. Okay, so if I set up intervals, okay, so you have 0. So you're going to have a bit of a binary situation. For the value x, it's either going to be negative, as in the case being among the values less than 0, or it is going to be positive, where we have among the values greater than 0. Okay, so we have, again, just test out r of x. Okay, so we got, for the test value x, okay, so we have here, when we select anything that is negative, we'll just go with -1. Anything that is positive, we'll go with 2. So you have r of x equal to 1 over 2x. So for r of -1, I guess you have 1 over 2 times -1. Okay, so that is going to go to -1/2. Now for r of 2, okay, so this will be 1 over 2 times 2. And this will come out to positive 1/4. And in the case of the sign of r of x, okay, so anything negative that is selected for the input, well, the output also winds up becoming negative. So you have the r of x is less than 0, and then anything selected that is positive for the input, the output is also going to be positive. So here you have that r of x is greater than 0. And so just looking at what we have, So I'm just going to repeat this. Okay, so for our scenarios, in case you have r of x or 1 over 2x is less than 0, again, no equal sign, so you have the exclusive use of parentheses. So for 1 over 2x is less than 0, or r of x is less than 0, again, we have between negative infinity and 0. And for 1 over 2x is less than or equal to 0. So again, you're heading in the same direction as r of x is less than 0. And again, we're still involving the limits negative infinity and 0. Again, infinities are boundless, so negative infinity stays in the parentheses. Now, we got the equal sign, and one might be tempted to put a bracket around 0. But the problematic situation is that the only 0 we have is not in the domain. So 0, once again, is going to be in the parentheses. And for 1 over 2x is greater than 0. Okay, so you have where r of x is greater than 0, so we're looking at, once again, positive values. Okay, so you have parentheses around 0 and infinity. Now for 1 over 2x is greater than or equal to 0. Again, we have between 0 and infinity. Again, infinity is boundless. And once again, okay, we've got the equal sign. However, 0, or only 0, is not in the domain. So it's like for all 4 of these cases, we only have parentheses for the grouping symbols. Again, because the only 0 we've been able to use to establish our tables is not in the domain to begin with. Okay, so no bracket in this one. All right, now just looking at sort of separating the wheat from the chaff. Okay, and so we have a rational function r of x, and we have is equal to x minus 4 we have all over x plus 2. Okay. So we have just our expressions in x. Okay, so we have in the numerator. Okay, so we have x minus 4. If I set this equal to 0, we have that x is equal to 4. And if x plus 2 is equal to 0, okay, so you have that x is equal to negative 2. So with r of x, I have x minus 4 over x plus 2. Now for the zeros, now we got 4. 4 comes from x minus 4, which is in the numerator. Okay, so 4 would set the rational function equal to 0. So you have 4. Again, this is going to be in the domain. And as for negative 2, okay, this stems from x plus 2. And if I set x to negative 2, I would end up with a 0 denominator. So instead of equaling 0, under that condition, the rational function would be undefined. Okay, so we're going to have for negative 2. Again, this is not in the domain. Okay, so you have the establishment of 2 zeros. And for what we have here, okay, so going from negative infinity, now between the two zeros, -2 is the smaller. Okay, so you have those values of x less than -2, and -2 is going to be bypassed. Where we have the next category, we're going to have those values of x greater than -2 and less than 4. And with 4, it's the higher and the last of the zeros. Okay, we have for the rest of the values x, we have those which will be greater than 4. So looking at setting up our table, so we got the process here. We have selecting test values of x and then testing out the rational function value for each input. Okay, so we have for values of x less than -2, we can go with -3. Between -2 and 4, okay, we can go with 0 once again. But you could, if you want to go with -1 or a positive number that is less than 4, they can select that value as well. And anything greater than 4, we'll just go with 5. Okay, so we're looking at r of -3. Okay, so for what we have here, -3 minus 4 is going to be -7. And -3 plus 2 is -1. So you have in the reduction, okay, this is going to go to +7. And for r of 0, so you have -4 over 2. And that reduces to -2. And for what we have in the case of r of 5, okay, this one, 5 minus 4 is 1, 1 plus 2 is 3, so right away, that's just going to be 5 plus 2 is 7. Okay, so you have 5 minus 4 is 1, 5 plus 2 is 7, so this is going to be a small positive fraction already in simplest form. And in the case of the sign of r of x, okay, so any input less than -2 is going to have a positive output for the rational function. Then from the middle category, okay, we have a negative output, so we have r of x is less than 0. And then for values of 4 selected, okay, for the input, the output is going to be positive, so we have r of x is greater than 0. Okay, so we have with our inequality scenarios. Okay, so we have x minus 4 over x plus 2. And see if I have, now this ratio is less than 0. Again, no equal sign, so no brackets in the intervals. Okay, so you have less than 0, so you're looking at between -2 and 4. For r of x is less than or equal to 0. Again, the equal sign indicates we could have a bracket, but just like in the earlier case, again, the only 0 we had was not in the domain of the function, so no bracket at all. Okay, so we had the same direction here as less than 0. And for the enclosure, now we have 4 is in the domain, -2 is not in the domain. So we are going to have a bracket thanks to 4 being in the domain. And for what we have in the other possibilities in the comparison to 0 inequalities, okay, so I have greater than 0, as well as r of x is greater than or equal to 0. Okay, now for the greater than 0, okay, so we're looking at the first and the last sets of limits. Again, no equal sign, so we have exclusively the use of parentheses for the grouping symbols. And for r of x is greater than or equal to 0. So you have the same limit values to group. Once again, infinities are boundless. So these will say in parentheses. And again, -2, that one is not in the domain. And for 4, 4 is in the domain. So just like in both cases, 4 sets or creates the equal to 0 part for this rational function. And so again, this is going to be in the bracket. All right. Now, there is one remaining portion here, and we have concerning comparison inequalities, not just in the sense of compared to 0, but where you might have two ratios compared to each other. And this one, I think the book goes a bit lightly on this, and I'm trying to recall. I think that Alex kind of has like a special case, and sometimes some of these comparison of ratios, inequalities, they can get pretty nasty. And I'll give you kind of a case here, and some of this stuff is going to be about like pulling teeth, but just kind of follow along. If I have, let's say, a couple of rational expressions, okay, and we'll say that we have 2 over x plus 2. Okay, so if I have 2 over x plus 2 is greater than or equal to 1 over x plus 4. Okay, and if you notice, you don't see the number 0 in appearance, okay, but I can make an amendment with this. Okay, so you have 2 over x plus 2 is greater than or equal to 1 over x plus 4. Okay, and what I can do here is I can just move the 1 over x plus 4. So we say we have 2 over x plus 2 minus 1 over x plus 4, okay, is greater than or equal to 0. Okay, and this is where it gets really tricky and really we start looking into the kind of the incremental elements. Okay, and I'll admit this is not one of my favorite exercises from chapter R, and that was like when you combine fractions that do not have the same denominator. And this one, I want to consolidate this as an overall rational expression, just kind of like what we've been working with from the start. Now, so I got this difference of terms, and if I have 2 over x plus 2 is subtracting 1 over x plus 4, okay, I want to put both of these ratios in terms of the least common denominator. Okay, so the quantity of x plus 2 times that of x plus 4. Okay, now I have 2 over x plus 2. And I have that part of the least common denominator, but missing is x plus 4. So I'm going to multiply this ratio by 1 in the form of x plus 4 over itself. Then we have subtracting. Okay, now we got 1 over x plus 4. And with the second fraction, I had the reverse scenario. I had the x plus 4 part, but missing the x plus 2. So I'm going to multiply this ratio by 1 in the form of x plus 2 over itself. Okay, so we'll have for both ratios. Okay, so we'll have x plus 2 times x plus 4 in the denominator. And for the numerator, okay, I can go ahead and distribute. So I have 2 times all of x plus 4, so that's going to be 2x plus 8. And we've got minus. Let's see. There we go. Okay, so we have for the second denominator. Okay, so x plus 4, x plus 2, same thing. B times A times B. Okay, and we have x plus 2. Okay, now, okay, so I've raised both fractions. Now, for the second numerator, okay, the terms will be affected all by the subtraction preceding this. Okay, so once I look at clustering, both of these fractions, which now are going to have, once again, the same denominator. Okay, so here we have 2x plus 8. And you'll have, okay, like subtraction is going to affect all of x plus 2. Okay, so we have throughout. Okay, so you have 2x plus 8. And x plus 2, we have negative x minus 2. Okay, we have all over the quantity of x plus 2 times that of x plus 4. Okay, and finally, as we combine the expression of terms in the numerator. Okay, so for what this will all come down to. Okay, so we have 2x minus x, so this will become x, and 8 minus 2 is 6. We have all over the product of x plus 2 and x plus 4. Let's kind of do a little bit of squeeze play here. Okay, so for this difference of fractions, and this is going to translate out to, again, the consolidated statement. Okay, so we're going to have x plus 6 all over x plus 2 times the quantity of x plus 4 is greater than or equal to 0. Okay. Right, and so this is going to be the comparison to inequality, or comparison to 0 inequality translation that we have with this comparison of ratios we started out with. Okay, so in looking at what we have for the resulting r of x, okay, so you have for r of x, okay, so you have x plus 6 you have all over the quantity of x plus 2 times that of x plus 4. Now for the zeros, okay, see like with x plus 6, okay, x plus 6 is in the numerator, and the 0 from this would be negative 6. So we can say once again that this is in the domain. Now for x plus 2, okay, so we have negative 2. And since x plus 2 is in the denominator, if I have a 0 denominator, again, the expression is undefined. And if x plus 4 is 0, okay, we have x equal to negative 4. Again, that would render the expression undefined. So negative 4 is not in the domain. And just looking at setting up, okay, our table of intervals. Okay, so we're going to have here, okay, so starting out of the trio, okay, negative 6 is the smallest amount. So those values of x less than negative 6, and then bypassing negative 6, okay, we're then going to have those values of x greater than negative 6 and less than negative 4. Then we have those values of x greater than negative 4 and less than negative 2. And finally, we have those values of x that will be greater than negative 2. Okay, so here we have kind of a wide table here because we have 3 distinct zeros and 4 distinct intervals established from them. So for test values we can apply for each section. Okay, so for anything less than -6, okay, we can go with -7. Between -6 and -4, if we still choose to go with integers, we can only go with -5. Likewise, okay, -4, -2 cannot be involved. Okay, so it has to be something greater than -4 and less than -2. And once again, we have only one integer that can be selected, and that is -3. And then anything greater than -2, okay, we can go with 0. And again, with the established r of x is equal to x plus 6. We have all over x plus 2 times x plus 4 . Okay, so we have, in the case of r of -7, okay, you have like, what's going to be -1, and then you have -5 times -3, so you have -1 over 15, so r of -7, okay, this is going to be -1/15. In the case of r of -5, okay, you got -5 plus 6 is 1, and you got -3 times -1, so again, we're going to have, in this one, okay, so you have +1 over +3, so for r of -5, okay, so this is going to be a +1/3. And in the case of r of -3, okay, so you're going to have, in this one, -3 plus 6, okay, we have +3. In the denominator, okay, so we have -3 plus 2 is -1, -3 plus 4 is 1, so you got 3 over -1, so that is going to go to -3. And for r of 0, okay, so you're going to have 6 over 2 times 4, so that'll be 6/8, and that is reducible to a +3/4. Okay, so for the sign of r of x, okay, so anything selected for the input that is less than -6, the output is going to be negative. So we'll have r of x is less than 0, and then for the next we have a positive output, whereupon we have r of x is greater than 0, and then next we have a negative. Then we have r of x is less than 0, and then we have anything selected higher than -2 for the input, the output is going to be positive. Okay, so you have r of x is greater than 0, and so just sizing things up and how these conditions will be applied to what we had for the original inequality. Okay, so if you notice, okay, we start out with 2 over x plus 2 is greater than or equal to 1 over x plus 4. And again, wrote this translated in terms of a comparison to 0 inequality. And again, we had, upon combining the expressions, I had this part where r of x is this consolidated ratio. So for the solution to this inequality is going to be what will be the fruits yielded thereof, where r of x is greater than or equal to 0. And so for what we have for the solution, okay, so we have the same direction as r of x is greater than 0. Okay, now I'll copy this. Okay, so again, you had the same direction as r of x is greater than 0. So we've got greater than 0 here, and the limit values, okay, we have -6 and -4. Also, r of x is greater than 0, so we have it involving -2 and infinity for the limit values to also group. And just for the enclosure, okay, now we have the equal sign, so we're looking out to see if any brackets are going to be applied. Now infinities are balanced once again, so you have a parenthesis around infinity. Now for -6, -6 is in the domain, so that creates an equal to 0 situation. So this is going to be in the bracket. Now for -4, that is not in the domain, so the rational function would be undefined at x is equal to -4, and the same thing can be said for -2. The undefined situation at x is equal to -2. So those values are going to be in the parentheses. Okay, so this would be the interval solution for this inequality.